In today's talk, we're going to discuss some problems which you'll find in Chapter F, for which sequences defined recursively appear very naturally. So we'll start with the stamp problem. In the stamp problem, and I'm choosing numbers that are just slightly different from the ones discussed in the book, in the stamp problem we suppose that we have as many stamps as we want, but they come only in denominations of 1 cent, 2 cents, and 4 cents. And we wish to arrange these stamps in a row on an envelope in order to put a total of n cents. How many ways can we do this? Let me show you an example. Let's say that here we're going to use n equals 7. Let's start with a simpler one. Let's say n equals 3. We have our envelope, and in the future I'm not going to be drawing the envelope here. But here in the upper right, if we want 3 cents, we could put a 1 cent stamp and a 2 cent stamp. Or of course we could put a 2 cent stamp, then a 1 cent stamp. Now here order is going to matter, so these will be considered different ways to arrange the stamps on the envelope. And you'll see pretty easily that there's only one other way to get 3 cents. And that's just a 1 cent stamp, a 1 cent stamp, and a 1 cent stamp. Now this is the case for n equals 3. For any number n, you could count how many ways there are to put n cents on an envelope. Let's define some notation. We'll let a sub n be the number of ways we can put stamps on the envelope and get a total of n cents. And we can compute very simply. A1 is 1, you just have a single 1 cent stamp. A2 is 2. You could have, and I'll now, again, ignoring the envelopes, you could have just a 1 cent stamp and a 1 cent stamp, or you could have just a 2 cent stamp. A3, we've already seen from the envelopes here, is 3. What is A4? Well, we could have a 1, 1, 1, 1. We could have a 1, 1, 2. And of course, we have different rearrangements here. We could have a 1, 2, 1. We could have a 2, 1, 1. Or we could have a 2, 2. Or we could have just a single 4. So how many choices is that? That's 1, 2, 3, 4, 5, 6. The question is, how do we compute further values, A5, A6, etc.? Well, we want to talk about finding a recurrence relation for the stamp problem. Let's consider how we could get A5 without just trying to list them all. Well, I could start with a 1 cent stamp on the left. If I start with a 1 cent stamp on the left, how many ways can I finish it? Well, I need 4 more cents. So here I have A4 ways to finish my envelope if I start with a 1. What if I started with a 2? Well, then I need 3 more cents. So I'd have A3 ways to finish it. What if I started with a 4? Well, then I need 1 more cent, and I'll have only A1 ways to finish. And of course, that's only 1 because I would have to just put a 1 there. So I have 3 choices for what stamp to start with, and for each of those choices, I know how many ways I can finish up, A1, A3, or A4. If we go back to our table here, A4 was 6, A3 is 3, A1 is 1. So what I have is 6 plus 3 plus 1, or 10. Can we get a general recurrence relation for this problem? What if I want n cents? Well, if I start with a 1, I have a sub n minus 1 ways to finish that row of stamps. If I start with a 2, I have a sub n minus 2 ways to finish that row of stamps. And if I start with a 4, I have a sub n minus 4 ways to finish that row of stamps. So this will be a general recurrence relation. This will be valid whenever n is at least 5. As we saw above, if n is less than 5, the a sub n minus 4 won't make any sense, or it would just be 0. And now our sequence is uniquely defined by starting the way we did. A1, remember, is 1, A2 was 2, A3 was just 3, A4 was 6, A5 was 10, that was the 6 plus 3 plus 1. I'll just put these 4. We start our sequence with a 1, 2, 3, 6, and then this recurrence relation tells me how to get every term beyond that. Now, this stamp problem can be modified in a number of ways, and there are many exercises in the book that will have you modifying the stamp problem a little bit, but they can all be, for each one, you can generate a recurrence relation. We're not going to do this right now, but you might look at that recurrence relation and say, well, it's somewhat like the Fibonacci sequence where you had an equals an minus 1 plus an minus 2, or in the Fibonacci case, fn is fn minus 1 plus fn minus 2. Only here for a sub n, we have this extra term, a sub n minus 4. And so that goes way back 4 terms in the sequence. Can we do something similar to what we already saw that we could do for recurrence relations, which only depended on the first of the 2 previous terms? And the answer is certainly yes. I'll just describe it to you briefly. We won't do any examples right now. We can talk about those later this week. If you have a geometric sequence that satisfies this recurrence relation, say the sequence r to the nth power, you write down here r to the nth, r to the n minus 1, r to the n minus 2, and r to the n minus 4. And this equation will give you a 4th degree polynomial. Any numbers r that are roots of this, or that satisfy this 4th degree polynomial equation, will be geometric sequences that satisfy our recurrence relation. And just as we saw before, any linear combination of these will also do. So all we have to do is take all of our solutions, say there are 4, if we're lucky enough that there are 4 distinct solutions to that quartic equation, and then we set up a system of linear equations that will allow us to get the first 4 terms here to match the first 4 terms, which we already know that we have. It's a much more complicated thing, and of course solving quartic equations is not generally very easy, and you have many, many more special cases depending on how many roots this quartic equation has. So the principle is very similar to what we learned in the previous lectures about how to solve recurrence relations where a sub n depended only on the 2 previous terms, but it just becomes much, much more complicated algebraically.